Okay, we are finally at a part where we are going to get to doing integration algebraically. Okay, so we've done it graphically, we've done it tabularly, we've done it doing all these little tricks. And now here, we are going to make our biggest connection, because remember when I say, what is an integral is a limit. An integral is the area under the curve. And our third piece that our second fundamental theorem gave us is that an integral is an inverse of a derivative. And I'm going to give us a new word here. And this video is going to be a lot of me talking. We're not really doing that much. I just need you to kind of soak in the information. So listen to this as much as you need to until it's properly absorbed. But an antiderivative, that is another word for an integral. When I say an integral is the inverse of a derivative, an integral is an antiderivative. And this is where we get to that notation that I kept harping on people about and taking points off, where there's a difference between capital F and lowercase f, because capital F, or capital whatever letter, is the notation we use for an antiderivative. And so what is an antiderivative? An antiderivative of f, of lowercase f, is another function, capital F, whose derivative is f. And that's just a lot of words. What that means is if we have our antiderivative, or if we have our function is 2x, the antiderivative of 2x is x squared, because the derivative of capital F is 2x. So because the derivative of this function gives us that, these are antiderivatives to each other. Okay, those are just some examples. And now let's go into notation. And this first piece is going to be have a really essential thing here. What is the derivative of x squared plus 1? Go ahead, answer it. Should take like 5 seconds. You should get that the derivative is 2x. Well, what happened to this plus 1? Well, the derivative of constant is just 0. We need to keep this in mind when we're thinking about antiderivatives. So we're going to come here, and there's 3 ways I can read this. I'm going to say all 3 of them to you, and then I'll tell you which one I'm most going to use most of the time. The first way is I can say, what is the indefinite integral? And it's indefinite because there's no bounds. There's no number here, no number there. What is the indefinite integral of 2x dx? So that's way 1, talking about it as an indefinite integral. The second way is I could just say, what's the integral of 2x dx? If I just say integral, that's implied to be indefinite, truthfully. So I'm honestly really never going to say, or very rarely going to say, what's the indefinite integral, unless I really want to hammer home a point. And then finally, the third way is, what is the antiderivative of 2x with respect to x? And I'm probably going to bounce back and forth between integral and antiderivative. Truthfully, integral is more natural to me, but based on reading stuff, I think antiderivative will be more helpful in your understanding. So I'm going to try to say antiderivative as much as possible. So what is the antiderivative of 2x? Well, I already sort of gave that one to us. The antiderivative of 2x is x squared. But there's another piece here that I really want to add that's going to be super important. And a ton of y'all are going to forget it and you're going to lose points, and I already know it's going to happen. But I want to emphasize, really strongly emphasize, listen to what I'm saying. When we take the derivative, the constant goes away. Here, we don't know if we have a constant, so we are going to add a constant. Maybe that constant is 0, maybe that constant is 2,337,642 million. I don't know, some crazy number. We're going to add a constant. So we're going to call that constant c, and that is our constant of integration. So the antiderivative of 2x is x squared plus c. And this opens up that a function can have a lot of antiderivatives. So here, up here in this example, I said the antiderivative of 2x is x squared. The antiderivative of 2x is x squared. The antiderivative of 2x is x squared plus 1. The antiderivative of 2x is x squared minus 3,647. Anything that has an x squared plus a constant is an antiderivative. So just keep that in mind. This plus c, you need to write it. This constant of integration is important. If you forget it, you will lose points. Okay. And now, coming here to this third one, what is the antiderivative of g prime of x? Well, that's just going to be g of x plus c. The antiderivative of g prime is g of x, and this comes back to our fundamental, one of our fundamental ideas of an integral, is that an integral and a derivative are inverses. They undo each other. So we can see here, we saw it with the second fundamental theorem of calculus, and we're seeing it here now. If we have an indefinite integral of a derivative, they just undo each other, and they take us back to our original function. Okay. Moving down, antiderivative rules. Every single derivative rule has an antiderivative rule. I'm going to take this time and I'm going to cram you in with all the derivative rules that I didn't super go over, but we kind of went over, and what their integral analogy is. So, starting with all of our polynomial rules. Well, this is our power rule. We're all very familiar with this rule. As long as n is not -1. I actually want to note that there. N is not equal to -1. That has a special situation happen there. Okay. So our power rule says that x to the n, the derivative of x to the n is n times x to the n minus 1. Well, what is the integral of that going to be? What is the antiderivative of that going to be? Well, we're going backwards. So let's think about what happened to our exponent. Well, our exponent was subtracted by 1. So instead of subtracting by 1, we are going to add 1. We're just going backwards. So we're going to add 1 to our exponent. And then what also happened, well, our original exponent became a coefficient. So we need, and when I say coefficient, I mean we multiplied by our original exponent. So what we're going to do is we're going to take our original exponent, which is this n plus 1, this is our original exponent, and we're, instead of multiplying, we are going to divide. We are just doing the opposite. We are doing the inverse. So our antiderivative of x to the n dx is x to the n plus 1 divided by n plus 1 plus c. Every time we take an indefinite integral, we're going to have a plus c. Okay, these other rules I'm not going to spend as much time on because they're sort of implied. K to the x, well, x just goes away. It just becomes our constant. So our integral of k is k to the x plus c. Just how we did, and I sort of showed this earlier when we were doing it, but we can apply it here as well. We have a derivative rule where if we're taking the derivative of something plus something, we can split that up, the derivative of the first thing plus the derivative of the second thing. We can do that same thing with integrals. And we can write this as the integral of f dx plus the integral of g dx. And I showed that earlier when we were doing one of the other videos. I forgot. I said it was a rule. And then this one also I showed you the integral rule, but I haven't formally shown you the derivative rule. But if we have a derivative with a constant times our function, we can pull that constant out and just take the derivative of the function. And the same things happens here with integrals. We can do a times the integral of f of x dx. We can pull that constant outside of the integral. Okay, there's our polynomial rules. Now we'll look at our exponential and log rules. So we have the derivative of natural log of x is 1 over x. Well, then the antiderivative of 1 over x is going to be the natural log. And another thing you might lose points for here it's the antiderivative is the natural log of the absolute value of x. That has to sort of do with the domain of our function. I don't want to say too much about it, but if we look here, natural log, it has a domain from 0 to infinity, but its derivative, 1 over x, that is defined everywhere except at 0. So when we take the antiderivative of this, we need this to be positive. We're only talking about the positive. It's complicated and hard to explain, but it has to do with the domain of the function. I'll just leave it at that. The derivative with respect to x of e to the x is e to the x. So the integral of e to the x dx is just going to be e to the x plus c. And then here, I didn't give you this derivative rule. I don't think it's going to come up that much, but just in case it does, the derivative with respect to x of a to the x is a to the x times ln of a. And the integral of a to the x dx is a to the x divided by ln of a plus c. And again, I won't spend too much explaining it, but I'll just say a little bit more. Here, the derivative of the a to the x is a to the x times ln of a. And the reason that ln that happens is it really happens here too, but what is the natural log of e? That's just 1, so that just goes becomes invisible. Here we have a natural log of a. We multiplied by the natural log of a, so when we do the antiderivative, we're dividing by the natural log of a. Okay, and there's our exponential rules. Now our trig rules. We have a lot of trig rules, and we have 6 big trig rules that I'm giving you now. The derivative of sine is cosine, so the antiderivative of cosine is going to be sine of x plus c. The derivative of tangent is secant squared. The derivative of secant, or the antiderivative of secant squared is going to be tangent plus c, and so on. So like all of these, I'll pause the video and fill out the rest of this because I don't need to spend time here going over all of this, but and antiderivatives and derivatives are inverses. So if we take the derivative of secant, we get secant tangent. Well then, if I'm taking the integral of secant tangent, it's going to take me back to my original function, to secant. So I'm going to fill all this in. I'm not going to talk through it, so when I come back, you'll have all these filled out. And these are things that you also just kind of need to memorize. Okay, I'm back, and all of these should be filled out. They're following there. You can pause this and study this and look at it, but I'm moving on. Then to our inverse trig rules. For now, I'm only focusing on these 2 inverse trig rules. Sorry, I was. And these are the last 2 rules that I'm going to give you. Then we're going to move on to doing some practice problems. Okay, so the derivative of arctan, which is tan inverse, is 1 over 1 plus x squared. So the integral of 1 over 1 plus x squared dx is going to be arctan of x plus c. And then, of course, arc sine, 1 over square root of 1 plus x squared. So if we integrate that, if we take the antiderivative of that, it's going to give us arc sine of x plus c. And you should know the other ones as well. You should know cosine inverse, all the other ones that I gave you. I think I gave you more than just the 3. But for now, these are the 2 that I'm putting in this video. Okay, now give me a second. Let me pull up my practice questions. And I'm just going to let this video run along. I wasn't sure if I wanted to split this video into 2 parts or just do one video. And I think I'm just going to do one long video. So let's say find a function whose derivative is f prime. Actually, let me just write it this way. Variables. F prime times g plus f times g prime. Okay, so this is my first example question. We want to find a function whose derivative is f prime times g plus f times g prime. Well, this should look familiar to you. This should look like our product rule. So what function would give us a derivative of this? I'll give you, you can pause the video, give you a few seconds to try and figure it out. Okay, and our function would actually just be f times g. F times g would give us this one right here. So that's the first one. Just thinking about derivatives. What function would give us a derivative of this? Okay, second question. Same question, find a function whose derivative. So I'm not gonna write that part out. And we want to find a function whose derivative is 5 minus 2x plus 3 cosine x. Or actually, here's how I'm going to write it. Is it syncing? Oh, there we go. I want to find a function whose derivative is this. So really what I'm going to write this as, I'm going to write this as the integral or the antiderivative of this. And we can use some rules here to actually make this a little nicer for us. This is the integral of 5 minus 2x plus 3 cosine x. Well, one of our polynomial rules up here let us take things that were being added or subtracted. This works for subtraction too. I really should put a plus or minus. And we can split it into pieces. So I'm just going to look at each of these pieces. And then again, I'm also going to look at, I'll remember this rule, the integral of a constant, the antiderivative of a constant is that thing times x, that constant times x. So I'll just let you remember the rules. I want you to try and do this on your own, pause the video, and when I come back, I'll talk us through it a little bit. Okay, so I'm breaking it into pieces. The antiderivative, oh, I forgot something. Y'all should have, hopefully you were screaming at me. I forgot the dx. Okay, but our first one, the antiderivative of 5, well, that's using our first rule. We're going to have 5x. And this is one integral, so I'm saying this now, I'm going to put 1 plus c all the way at the very end. So after I've done this whole integral, then I'm going to put the plus c. I'm not forgetting it. So our first part is going to be 5x. And then we have negative 2x. Well, this is going to be using our power rule, our integral power rule. So I'm going to take this exponent, or this coefficient, and I'm going to put it as an exponent plus 1. So I'm going to have x cubed. Or actually, let me give myself a little bit more space because we're going to do something interesting here. So we have x cubed, and then I'm dividing by this original exponent. So it's going to become negative 2/3. I'm going to put my division as a fraction here. So we have negative 2/3 x cubed. And we can check ourselves really quickly. If I say, what's the derivative of this? Well, if I move this, if I use the power rule, the derivative power rule, the derivative of this will give me 2/3 x squared times 3. Well, dividing by 3 and multiplying by 3, those are inverse, multiplicative inverses. And that just goes to 1, and it would give us this part right here. So if I take the derivative of this, it should give me that. Okay, and our last one, 3 cosine x. So this is going to be plus 3. The antiderivative of cosine is just going to be sine. And I can check myself again by saying, if I take the derivative of this, does it give me that? Well, the derivative of 3 sine of x is 3 cosine x, so we're good. Except we're not good because we're missing our thing. We're missing our plus c. And boom, this is our antiderivative right here. We just integrated 5 minus 2x plus 3 cosine x dx. Okay. Okay. Next one. Question 3, practice 3, we're going to do the integral of 9 minus 3x squared plus the square root of 7 cosine x dx. So I'll let you sort of try this one out on your own again. And then when I come back, I'll talk us through it, but I'm going to talk us through it pretty quickly. So have an idea of what the answer is when you come back. Okay, we're coming back, and I'm going to move quickly. The antiderivative of 9, that's just going to be 9x. The antiderivative of negative 3x squared, well, I'm going to take my exponent and add 1, so it's going to become x cubed. And then I'm going to divide by this same exponent. So dividing by 3, 3 divided by 3 is just 1, so we're left with negative x cubed. This is just a constant. So plus the square root of 7 times cosine x. What is the antiderivative of cosine? We already did that one. That's just sine of x plus c. And boom, the integral of this is just that. It just making connections between, if I differentiate this, will it give me that? What is the derivative of 9x? 9. What is the derivative of negative x cubed? Negative 3x squared. What is the derivative of the square root of 7 sine x? Square root of 7 cosine x. Boom. Okay, question 3 done. Da, 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 da. Okay, question 4. What is the integral of 2 over 1 minus the square root of 1 minus x squared dx? And this should look very similar. This one I'll actually go through it. We'll go through this one together. Although you can pause it and try and do it on your own, but I will talk our way through this one. Okay, so this looks similar to something to me. It looks similar. Oh shoot, where'd it go? To my arc sign, but my arc sign only has a 1 on the numerator. So how do I do that out? Well, this 2 is just a constant. Let's just pull it out. using our integral rules, our antiderivative rules, and we can rewrite this as 2 times, if it'll, oh, I forgot to press the button, 2 times this integral right here, and this is just our arc sine, so this equals 2 arc sine of x plus c. So just using our integral rules. Okay. This next one is going to be a little bit of a challenge one, and we're actually going to spend time doing questions like this and figuring out a real method. For this. But right now I just want to sort of see, I'm sure some of us can figure it out. What is the antiderivative of 3x squared times e to the x cubed? And right now we don't have a procedure for this, but take a guess. Try and figure out what this antiderivative would be. Okay. I'm not going to give it, there's a tool that we have that can help us with this a lot. I'm not going to give us that tool yet because I want to spend I want that tool to get to shine because it is a powerful tool. But I'm just looking at this and I know that the derivative of e to the u is itself times the derivative of u. Well, the derivative of x cubed is 3x squared, so this is actually just going to be our e to the x cubed plus c. Because if I take the derivative of e to the x cubed, that gives me e to the x cubed times the derivative of this right here, which is 3x squared. Okay. All right. Next one, let's look at some trig. Again, this is something that I'm going to give us a tool for, but right now I think we're still okay. 3 cosine of 3x dx. Okay, so now we don't just have an x, we have a 3x here. Well, let's start with this cosine. What is the antiderivative of cosine? The antiderivative of cosine is just sine. So we're going to have a sine of 3x. And let me just think about what happens when I take the derivative of sine of 3x. Well, it gives me cosine of 3x times 3. Well, that's where this times 3 is coming from. So I don't even have to do anything else apart from my plus c. So sort of just thinking about it backwards, the antiderivative of cosine of 3x would be sine of 3x, and if I take the derivative of this, it would give me that. So we're good there. Again, that same tool, we'll use the same tool for both of these. Let's just keep going. I don't know how many more I have on my list to do. 2 more on my list. Okay, so 7, I'll actually give this a little bit better notation, or a new way to ask it. Find h if h prime equals this. Okay. So find h if h prime equals this function right here. Well, remember, what is the relationship between a derivative and an integral? They're inverses. So if I integrate h prime of x with respect to x, that's going to just give me h of x plus c. So let's just integrate this whole function. So we're looking at the integral of secant squared of x minus 3 secant of 3x tangent of 3x dx. Okay. So pause the video, take some time, try and figure out this antiderivative on your own. All right, now that you've tried to do it on your own, we'll do it together. Integral, the antiderivative of secant squared, well, I know that's going to be tangent of x. And then we have this negative 3 secant 3x tangent 3x. That, to me, looks something like secant of 3x. So I'm just going to start by putting secant of 3x, and then I'm going to take the derivative and see if I need to change anything. Well, the derivative of secant of 3x is secant 3x times tangent 3x times the derivative of our inside, which is 3x. So 3 secant, and that gave us everything we needed. And so we just need a plus c at the end. Okay. And so h of x equals this function right here. And our last question I want to find the integral of 2 over 1 plus t squared minus t over 5 plus pi. And this time we're finding the antiderivative of t, so we have dt instead of dx. Pause the video, try and do it on your own. There's nothing super new here for this one. Okay, you've tried it on your own. This 2 over 1 plus t squared, well, we already did that earlier. That was like what we did over here, except it was x instead of t. And that was 2 arc sine of x. So this is just going to be 2 arc sine of t minus, and this t has an exponent of 1, so we're going to raise that to a 2. And we're going to have a t squared. And then we're dividing by that same exponent, so dividing by 2. So we have t over 5 divided by 2. That's going to end up being t squared divided by 10. And then this is just a constant, so plus pi x plus c. And we're finally at a part where we can actually find integrals now by thinking about them as antiderivatives. I hope this video is helpful. We have one more video, I think, for this unit, and then we're done. 1 or 2 more. All right. Thank you for watching.